Hey everybody, my group is myself, Noah Williams, Ryan McCaldon, and Gabriel Vasquez. And our final project focused on arsenic as a pollutant in aqueous systems. What we will cover today will be a brief introduction into what arsenic is and why it is important in aqueous systems, sources of arsenic pollution. So where does arsenic come from? And then we'll dive a little bit deeper into the geochemistry and also what amount of environmental remediation is going on. So what is arsenic? Arsenic is a heavy metal pollutant. So what that means is that it is 5 times denser than water. Furthermore, arsenic is a metalloid, so it can form as a metal, but it can also form other species. Gabe will touch more on that later. And then finally, arsenic has multiple oxidation states, and Gabe will also talk about that in the geochemistry portion. So why is arsenic important? Arsenic is important because it poses significant health risks to us. So arsenic is a carcinogen, and it is classified by the International Agency for Research on Cancer as a group 1 carcinogen. At high enough levels, arsenic also can give you arsenic poisoning, which is pretty bad. One of the symptoms is bloody diarrhea, so generally not good. But aside from health risks to humans, it also poses environmental concern. The reason it is so lethal to humans, that also applies to other fauna and also flora that this arsenic polluted water kind of is a part of. And it is also subject to bioaccumulation. So sources of arsenic pollution stem from arsenic being a naturally occurring mineral in the earth. And what happens is that there is mining, which accelerates the path for arsenic to get into our aqueous systems. Aside from naturally occurring arsenic, arsenic is also used as a pesticide, herbicide, and insecticide, or at least it has been used in the past. It is also used as a wood preservative, but with all this sides, like herbicide, pesticide, you would think people would realize it's not great for the environment. So I'm just going to give you a brief overview of how mining affects the amount of arsenic within an aqueous system. So what happens is there's naturally occurring arsenic as some mineral, and then the mineral is weathered, and you are resulting in an arsenic-rich soil, and then more weathering and transport, and then these soluble arsenic species are then deposited in an aqueous system, some like river. And what mining does is that it accelerates this weathering process. And it does this from essentially just more exposure that these minerals are getting to weathering. And so that increases the amount in the soil, which in turn increases the amount that's ending up in our waters. Gabe is going to now talk about a little bit more about the geochemical side of arsenic.
Right, so to, I guess, better understand the processes of arsenic, we have to take a closer look at the geochemistry. Arsenic's a redox sensitive element, so it means that it's generally soluble through a range of pH values and is both in oxidizing and reducing conditions. The oxidation states can occur as -3, which is common in arsine gas, stemming from reducing environments. It can be uncharged, which is generally uncommon, +3, which is known as arsenite, and +5, arsenate. Speciation is how the element shows up in the environment. So arsenic is going to be in different phases depending on the conditions. For soluble anionic forms, arsenate and arsenite are common in rocks and superficial environments, while ophromite is found in low temperature hydrothermal veins and hot springs. And realgar is one of the leading ores of arsenic. As for iron arsenic sulfides, we have arsenopyrite, which is a metal-bearing sulfide mineral that's unstable in oxidizing environments, where the sulfide ion is oxidized from -2 to +6. And that's dangerous because arsenic can be released into soils, like Noah was talking about, or groundwater. Complexes are formed between arsenic and colloidal iron oxides, or dissolved or particulate organic matter. Arsenic ions can be absorbed onto the surface of other metal oxides or clay minerals, like silica, aluminum, iron, titanium, because they easily can fit or have similar charges. Here's a basic EH-pH diagram. Different phases of arsenic are going to be plotted here based on their stability in various conditions. The upper and lower limits show the stability of water. Near the upper limit, you're going to find environments in contact with the atmosphere. So you're thinking about oceans and streams. And so those are the oxidizing environments where you're going to typically find these phases. Down by the lower limit, you're going to find conditions that are isolated from the environment, like from the atmosphere, like deep marine environments or waterlogged soils. These are the reducing environments where you're likely going to find these phases. The vertical lines show acid-base reactions, and horizontal lines are generally redox reactions. But let's look at the chemical reaction we have on the left, and let's say we have arsenopyrite, which is stable in reducing environments, and it comes in contact with water. This is going to oxidize it, which raises the oxidation reduction potential and decreases the pH, leaving us with arsenic acid, or arsenic acid. Finally, arsenic interacts with the materials and fluids around it. Precipitation and dissolution can be pretty slow because it mainly involves the structural ions. In absorption, arsenic often binds to the surface of metal oxides like we talked about, and also to clay minerals, but it depends on the concentration of arsenic and what else is competing for those spaces. For co-precipitation, ions can be scavenged when a mineral is forming. For example, arsenic can be incorporated into the formation of pyrite. And yeah, that's my little breakdown. Hopefully it helped. Ryan's going to talk about how these processes are affecting the environment.
Ryan, can you, are you talking?
So the most extreme example of arsenic remediation in in human-caused means is probably Giant Mine in Northwest Territories, Canada, when this mine closed down, there was more than 200,000 tons of arsenic trioxide powder left stored in this chamber pictured on the right-hand side. You can see how it looks. It obviously can't be removed because it's like the size of flour particles. And it's soluble in water, so it will move. Go on. In order to remediate this mine, the plan that was decided on is called the freeze block method. Essentially, what the Canadians decided to do is to utilize ice rink style technology to build coolant pipes all around the outside of this storage chamber. And then they froze it. And then they dumped a bunch of water into the chamber and then froze that too. So there's essentially just this giant block of arsenic ice underground in this part of Canada, which is all right. The ground all of these technical difficulties. So the area where this is located is already under permafrost ground. So the area is expected to remain frozen, and then they're cooling it to make it more frozen. As far as actual water treatment goes, once the arsenic gets in there, it's very difficult to remove. Some is removed, a significant amount is removed when calcium and magnesium is removed from the water. But the biggest difficulty is that there's also significant levels of neutral arsenic 3 in the solutions, and that's very difficult to remove. It essentially has to be converted to arsenic 5 through oxidation methods, and then that can be removed through filtration and coprecipitation methods. This is very difficult to implement because this is very expensive. The kinds of places where this is very big are very poor regions, like Bangladesh and West Bengal, India have some 120 million cases of arsenic poisoning ongoing right now. But the University of Berkeley has developed a new method of removing arsenic from water, which they are deploying in India, called electrochemical arsenic remediation, which has steel plates in water, and then they apply a current to it, which causes essentially rust particles to form in the solution, which will, while they're being formed, they will take up arsenic particles and precipitate them out as well as oxidizing arsenic 3 to arsenic 5. So it sort of does the whole shebang in one go.
Questions?